In the previous video, I constructed a peak model to fit this sulfur 2s data. The line shape was an LA90, so this is a Voigt function that is formed by integrating a convolution between a Lorentzian and a Gaussian over a range of energies, and it produces a line shape that is sympathetic to this sulfur 2s signal. I also accounted for the background by introducing a component that was calculated from the line shape, and this represents inelastically scattered signal that is due to this photoemission peak. And then a third component represented the offset in intensity that was a result of inelastic scattering from photoemission peaks with higher kinetic energy. The problem is that we may not have the optimum peak model for these data. It's very good, but it's not necessarily the optimum one. And when we want to choose from a set of line shapes, we would like to have some way of scanning the parameter that varies the shape of the LA line shape, and then from that scan choose the best possible for the data. And there is an option on the Quantification Parameters Dialog window on the components property page that does precisely that. If I choose the line shape parameter for one of the components and then press the Test Peak Model button, what I have is an option to scan the parameter of a line shape. So if I change the parameter in the LA definition using square brackets to indicate an interval, so I've just entered 70 to 99, and this will produce a scan of the line shape parameter for peak models that will be then fitted to the same data. This will give us a range of different fitting statistics, and we can evaluate how the peak model is fitting the data to make some educated decision about what line shape is most appropriate for this particular peak model. Now, there is a subtlety here in that I've got a component that represents the inelastic scattering from the photoemission peak using the same line shape. So I've indicated here that I've got the same component index 1 in both of these components, and there is an option for causing the scan of this parameter in one component to apply to any other components in the peak model. And there's a special trick here in that if we've got a component that is constructed from a Shirley response to that component, then when I scan this parameter and I assign it to these different components, what will happen is that the LA line shape will apply to the photoemission peak, and it will be updated in the Shirley response to that photoemission peak. So let's see how that works. So I'm going to perform this scan by pressing OK. It just checks with me that I've got the scan that I want, because sometimes this takes a bit of time, and then I press yes because it is what I want, and the result is a new file, and in the file I've got a set of spectra. They're all identical, and what's changing in each one of these VAMAS blocks is the peak model, and I'm adjusting the line shape parameter. I'm also collecting the figure of merit, so we can see here the figure of merit. If I adjust the display on the y-axis, you can see this is the root mean square. That's because I had a root mean square tick box ticked on the Quantification Parameters Dialog window component property page. If I untick that, that would be a chi-square, but this is sufficient. We can see now that the scan is producing a minimum, and the minimum is somewhere about 90. So it's not surprising that I chose by eye the parameter to be 90. But I could improve on this by simply using this technique to work out the optimum line shape for the given fitting statistic, the given model, and the given data.